Okay, we're going to start our second video. And in the second video, we're going to talk about why we were interested in talking about second derivatives. Okay, because second derivatives help us determine something called concavity, which is a graph characteristic. When we talk about a graph having concavity, it's referring to the shape of the curve in the function. When we have a curve in a function, we might be looking at a curve that, ooh, that's a horrible picture. Let's pretend I didn't draw that. Let's draw an axis first. Okay, so XY axis, we might have a curve or a segment of a curve that looks something like that. We might have a curve or segment of a curve that looks something like that. Now, those are both increasing curves. They both have a positive slope. But this slope, or this curve, the one here on the left, is considered concave up. It's kind of like if I put two eyes there, you could kind of see a smiley face. Versus this curve, considered concave down. Now, what makes a curve concave up versus concave down has to do with how the slope is changing. So like this guy has a positive slope. And if I were looking, if I maybe could pick some numbers and that would make sense for this graph, if I had 0, 1, and then maybe 1, 2, and then 2, 5, and then 3, 10, that would make a concave up function. Because if you look at how it's growing, the increase is increasing. The y's are getting bigger, and the amount by which the y's are getting bigger is also getting bigger. That creates a concave up increasing curve. In a concave down curve, increasing still, if we had something similar like 0, 1, then we might have 1, 2, but then we might have 2, 2.75, and then we might have something like 3, 3.5, and 4, 4. And so you're like, well, what's going on there? Well, the y's are still getting bigger. But let's look at by how much they're getting bigger. Bigger by 1, bigger by 0.75. I actually made this the same, 0.75. And then bigger than by 0.5. So we have a y getting bigger. So we're increasing. But actually, if I try to model how I wrote it over here, I would say my amount of increase is decreasing. And that makes the curve, when it's rising, curve that way versus that way. The same thing can happen with decreasing curves. We have can have the same kind of concavity. If I have a curve like that, decreasing, but still concave up, versus decreasing and concave down. It's interesting how in the increasing picture, the increase is gets steep, goes more quickly. Here, the increase kind of slows down. In the decrease here kind of slows down. This decrease goes really fast. So, the things that make our polynomial functions curvy and have turns, have different concavity. That's what we're looking at analyzing here. And how we can figure this out, we can figure out concavity of a particular graph from the second derivative. Okay. The good news is it's really easy because it's essentially almost identical to the same process for increasing and decreasing in relative maxes and mins. It's just using the second derivative. All right, so we're going to do an example of identifying concavity. And when we're all done, we'll look at a picture of the function to see what we expect, if what we predicted actually happened. So let's take x to the fourth minus 10x squared for our function. In order to identify concavity, I need the second derivative. All right, so first derivative. Second derivative. Oops. I lied. I'm going to change this. Everyone's like, no. Why? Because I want it to work a certain way. Sorry. Let's do that. I know you'll forgive me. Okay. I wanted to get a certain kind of number, so I wanted to manipulate this a little bit. So here's my original function. Yes, I changed it. Here's my first derivative. Here's my second derivative. Now what am I going to do? I'm going to set my second derivative equal to 0 and get critical values. Critical values for the second derivative. I hear my dog coming. Okay. So there's my second derivative. Nice little factoring, if you don't recognize that. And I get 2 critical values. Sometimes we'll get 1, sometimes we'll get 2, sometimes we might get none. Now, I bet you can guess what we're going to do. We're going to build a number line. We're going to put those critical values on the number line. This is going to be a number line about f prime, or excuse me, f double prime, because here's what we're going to know. When we get f double prime greater than 0, or positive, that means that part of f is concave up. And when f double prime is less than 0 or negative, that means that part of f is concave down. So, I got my number line. I got my second derivative. I'm going to put in my numbers. I'm going to get a lot of alternating behaviors still. A big number, something bigger than 5, everybody would be positive. Something between them, like a 3, would make a negative. So here's what I know. I know f is concave up from negative infinity to 0 and from 5 to infinity. I know f is concave down from 0 to 5. And this is the last thing. At x equals 0 and x equals 5, those are called points of inflection. To have points of inflection, f double prime has to change sign. You have to get a change in concavity to have a point of inflection. All right, so let's see what this looks like. Let's see if I can remember what we did. Of course I did. What is it? 4x cubed minus 30x squared. Okie dokie. 4x. No, that was my first derivative. Back it up. Hang on. Wait a minute. X to the 4th minus 10x cubed. We've got to make sure we're graphing f if we're going to want to see this. X to the 4th minus 10x cubed. Now you might be like, wait a minute. Let me scroll back. Actually, let me see if I can get us a better window. Still not great. Oh, I know. I remember I have this trick. I love that trick. Here, remember to show you guys that trick. Okay. So here we go. What did we say? We said, remember we didn't do increasing, decreasing. We just did concavity. We said it was going to be concave up until 0, and then it was going to go concave down from 0 to 5. Well, this is definitely concave up-ish, and then it turns to concave down-ish. And then here's the interesting part. This part can't really see on the graph. You could just kind of eyeball it. This is definitely the little concave down part, because that's a little frowny. And this definitely gets smiley, but it's hard to eyeball where that changes. And what the calculus has just told us is that exact change, when it's stopping from being concave down and starting to be concave up again, is at 5. Concave up, concave down, concave up, and it's concave up the rest of the way. Okay. You're going to practice this with the problems on the worksheet. There are a couple special situations that I'm going to show you. I'm going to make a third video to show those. But hopefully with what we just went over on this problem, you can try some of the first problems on the worksheet to identify concavity.